Before we complete the details, let's just note that we have a temperature that is maximum at the origin and gets lower as we move out toward the surface of the sphere. The further we get from the origin, the lower the temperature. Where on this triangle then would the temperature be a maximum? Well, one would expect it would be at the point on the triangle that's closest to the origin. And by the symmetry of the triangle, we would kind of expect that to be at the intersection of the medians of this triangle. If we draw the midpoint here, here, and here, and draw this line, and this line, it's an equilateral triangle. They meet at this point, and that's going to be the closest point, so that our solution should be consistent with this idea, assuming that the median really is the closest point, and I haven't proved that. The point at which this occurs should be equidistant from all these edges because of the symmetry. Not sure that's the intersection of the medians. In any case, our del t function, and I guess we've just lost our focus. Come back, please. Here we go. Get more markers. There we go. And I'm not sure whether we lost that before or after I waved my hands over this, but let's move on. Okay, the del t is negative xi minus yj minus zk over this. The I component is negative x divided by the 3/2 power here. So we have, for the I components, negative x over 1 plus x squared plus y squared plus z squared to the 3/2 should equal lambda times del f, and del f is just I plus j plus k. The I component of del f is then just 1. And negative y over 1 plus x squared plus y squared plus z squared to the 3/2 should equal, again, lambda times 1. This being the j component of our del t, and 1 being the j component of our del f. Also negative z over 1 plus x squared plus y squared plus z squared to the 3/2 again equals lambda times 1. Our final equation is just f of x, y, z equals 0, which is x plus y plus z minus 1 equals 0. Now we have 4 equations, 4 unknowns, x, y, z, and lambda. Now these equations could be solved by brute force. For example, we could solve this equation for z, plug that in for z here, and z here. Then we would have 3 equations in x, y, and lambda, and we could proceed to attempt to solve those 3 equations. However, there's a much easier way in this case. This situation, as we've seen, has a nice symmetry, and that's reflected in these equations. So, at any solution point, we can get rid of those 1's if we want to, because of course lambda times 1 is 1. We'll get them back in a minute, but just to look at these equations, at any solution point, x, y, z, the denominator 1 plus x squared plus y squared plus z squared is the same for the first three equations. So whatever your solution point is, the denominators are all three the same at that solution point. Now, this means that negative x is lambda times that denominator, negative y is lambda times that denominator, negative z is lambda times that same denominator. Your conclusion is that negative x, get these straight, equals negative y equals negative z equals lambda times 1 plus x squared plus y squared plus z squared to the 3 halves. The key is that negative x equals negative y equals negative z, so x equals y equals z. At the solution point, using that with our third equation, we draw the immediate conclusion that x equals y equals z, so all three of these are equal and they add up to 1. And because the third equation, x plus y plus z minus 1 equals 0, is very easily rewritten x plus y plus z equals 1. So without crunching any numbers, doing any formal algebra, we can conclude that x equals y equals z equals 1/3. Now we know from the way we've talked about this function and just from looking at the way it behaves as we move away from the center that the function is going to be maximized, the temperature is going to be maximized at this point, but we haven't yet shown that in terms of our procedures for solving this sort of equation or this sort of problem. So the question first of all, 1/3, 1/3, 1/3 is an extreme, is a point at which t is a maximum or a minimum on x plus y plus z minus 1 equals 0 on the plane. The question is, which is it? Is it a maximum or is it a minimum? So here's our work, and we'll answer this question on a final clip here.